That's all I'm going to mention about it, because there are a few more things you need to know about modulated before you actually use it, but I won't be going into that today. So most people, again, will be using standard mode. Sorry. Most people will be using standard mode, and on the right hand side there would be a test type. So in here there are specific templates that are sort of preset for you to just use in terms of just running a pretty standard experiment. So the most basic one, or the most basic two, are isothermal, which, so to speak for itself, you go to a certain temperature and you hold it for X amount of time, right? But the one that will be more used will be the ramp. So when you click on ramp, you would see that a template comes up here where you're basically just going to be inserting numbers. Your starting temperature, again, we have a lower temperature of -90 and we go all the way up to 400. You don't need to run the entire cycle for everything. When you come in, you should have some idea of what your sample is going to do and where that might be. So select decent start and end values so that you capture what it is you actually come here to investigate. So for example, if I wanted to start at 0, or I didn't really care about my starting temperature because everything's going to be, you know, above room temperature, I can say use current. Use current basically means start at whatever temperature the furnace is currently held at. By default, or when the instrument is on standby, it's held at 35 degrees Celsius. So if I hit use current, that's about where you're going to start your experiment. If I want a different number, I uncheck that box and I type the number in here. So for example, I want to start at 0, I type 0 in this box, okay? And of course, final temperature, same thing. You have an upper temperature of 400. If you attempt to type anything higher than 400, it will, when you hit start, it will tell you that it can't do it. So it already has a secondary backup to tell you, you know, don't go above 400 Celsius. But remember, when you come in, that 400 is the maximum. So let's say I would like to go to 300 Celsius, that's okay. My heating rate, so how fast am I going to move between 0 and 300? Default numbers you would see in, for example, the ASTM standard, or in a lot of literature that you may read, would be 10, 20, and 5, essentially, degrees Celsius per minute. I like to start at 10 as a default, and you know, when I run my experiment at 10 C per minute, I look and see what's going on, what's not going on, and then I can make my decision afterward to do whether I want to slow it down, whether I want to extend my temperature range, etc., etc. So starting at 10 is not a bad place. It can sort of help you navigate through what else you may need to do for other samples. So once you put in these 3 numbers, you can look at the segments tab, and you would see these are the actual direct commands that it'll be sending to the instrument. The first one is an equilibrate function, equilibrate to 0, because I wanted to start at 0 degrees Celsius. Equilibrate basically is telling the instrument to go to 0 as quickly as you can, and then get as close to 0 as you can. So that generally means within a few % of the number that you type in there. So if you're going to 0 degrees Celsius, it won't move on to the other step until you get to 0.2 or something like that degrees Celsius. So it'll be pretty accurate in terms of your starting temperature, or whatever temperature you put in and as your equilibrate function. And then it will move on to the second step, which is the ramp at 10 C per minute to 300 Celsius. Okay? So it's a fairly simple sort of one-shot experiment. Typically, however, that's not what you need, or that's not all that you need. You need more than that. And if you look at the ASTM standards, they will tell you that you need at least 2 to 3 heating cycles in order to sort of properly analyze your data. You can do that here. There's 2 ways that you can do that. There's one that says heat, cool, heat, and there's another one that says cyclic. Uh, to start, we'll do the heat, cool, heat. So when you click on that template, you get an entirely some more numbers at least to fill in. And as the test type says, that's you're doing a first heating scan, then you're cooling your sample down, and then you're heating it a second time. So you're going to have 2 heating scans and 1 cooling scan that you can control. Now, as far as the numbers that are on here, if they're pretty logical. There's a start temperature again. So again, let's just say I'm starting at 0. I'm going to have my heating rate, it's 10 C per minute, my upper temperature, and then I'm going to have a cooling rate for my cooling step. Again, typically I like to keep the heating and cooling rates about the same number, at least to start with, until you know more about your sample. And then you can change these according to what you're trying to do. Remember that the heating and cooling rates do affect what's going to happen. So especially if your sample, for example, is semi-crystalline, by controlling your cooling rate, you can possibly control your crystallization kinetics, which means that you can control how much of your sample has crystallized. So be mindful of when you change these numbers, what's going to happen to the sample subsequently. They shouldn't really be randomly changed. You should have some reason as to why it is you want to speed up or slow down your heating and cooling rates. And then the very last number is your lower temperature, which is basically the temperature you would start your second heating scan at. So for this case, let's say I want to start at the same place, so I'm going to go back to 0. Okay. So now when I go to the segments tab, there's a lot more commands listed down here. The first one, like I mentioned, is 0 degrees Celsius, equilibrate to 0. Then we're going to ramp up at 10 C per minute to the 250 Celsius. There's a mark end of cycle. I'll explain what that means in a second. Then we're going to go down from 250 Celsius at 10 C per minute back down to 0 degrees. And then we're going to go back up from 0 to 250. So heat, cool, heat. All right. So that's exactly what you'll be doing here. The mark end of cycle command is, although the instrument possibly does this automatically, the mark end of cycle essentially takes this one file that everything's going to be saved as or saved in and sort of splits it up into little subfiles. This comes in handy when you're doing your post-analysis. Instead of having, for example, in this case, you're going to have 2 heating scans. They're very likely going to crisscross each other and overlay each other and do other weird things. And so when you go into your actual analysis, you won't really know, or you won't necessarily be sure which one you're analyzing at what time. So the mark end of cycle helps split these individual steps into sort of mini subfiles that you can pull out individually to analyze each step by itself without the crisscrossing of other steps over it. Okay, so it just helps sort of make things a little bit neater and helps you not be as confused when you're doing your post-analysis. Again, I believe that the instrument does this automatically whether or not you have the mark end of cycle in here, but it's also good practice to put it in there just in case anything happens. So in this case, you have these 3 steps: heat, cool, heat. Like I said, in this case, you are controlling your cooling step. So be mindful of the heating or cooling rates that you're doing in order to control whatever it is may be happening to your sample as it cools down, whether that be crystallization or vitrification, turning into a glass, etc. So while we're on this, I want to sort of mention the fact of doing 2 and 3 heating scans. So this is actually pretty important because DSC is sort of defined as a bulk technique, so a bulk analysis. So you're analyzing sort of the general properties of your material. However, typically when you first get your material, or especially if you're making your own material, it's not necessarily going to be in the configuration that it likes. A good example of that is when you're doing polymerization, for example. Typically your last step for making a polymer is precipitating it in a non-solvent. Of course, it's a non-solvent, so the polymer doesn't actually like to be in there. So when you take that polymer out and you dry it and filter it and whatever else you do, it's not going to be in a very comfortable configuration, because essentially once you drop it into that non-solvent, it's going to just shrink up. Now, when you come and take that material and place it in the DSC, when you run your first heat is going to be depicting that sort of shrinking up and crumpling up behavior that happened during that synthesis process, of which you really have no control over. All right. So the first heating scan shows what's typically defined as thermal history of the sample. So, like in the case of synthesizing your material, that thermal history is going to be, dropping it in that non-solvent and doing all the drying and all these other things that you did to it. If you bought your material, for example, is going to be the stresses of doing things like molding or even 3D printing, extrusion. All these things create different configurations or force the polymer into different configurations, such that all of that's sort of going to be depicted in your first heat. Now, if you care about that, so if you're doing something like 3D printing, for example, and you care about looking at the configuration of the polymer as soon as you've physically made it, then your first heating scan is going to be very important to you, because that's where all of that information is going to be stored. Now, if you don't care about that and you just want the bulk properties of the material, the first heating scan may not be very useful to you. So in a lot of publications and things like that that are looking at DSC, you would see that they only analyze either the second or the third heats, because that first heat is almost always tossed, because they don't really care about what happened before they put it in the instrument. They only want the bulk properties. And so that first heat basically erases all of that stuff that happened before you put it in the instrument, and then your cooling scan would then impart a known thermal history, which will be detected by how fast you heat or cool it down. And so that way you can predict, or at least better predict, what's going to happen in the subsequent heating scans. Okay, so that first heat is always sort of chalked up to thermal history. Again, of course, if you actually have physical control of your thermal history, then the first heat may be more important to you. If you don't, then it may not be important to you at all. That's a sort of a decision based on the sample that you're trying to do and the information you're trying to achieve. But that's basically what and why you would see a lot of publications and the ASTM standards talk about doing multiple heating cycles, because you want to erase that thermal history. So typically the second heating scan would give you something that's close to the equilibrium of the sample or the material with equilibrium conditions. The third heat, if you chose to do it, is typically for repeatability. So you want to make sure that whatever you saw in the second heat is the actual properties of the material, and you also want to make sure that the material itself didn't transform in some way, whether it may have degraded a little bit, or some property that you saw in the second heat somehow doesn't show up in the third heat. That's a consistency issue that you would have to possibly explain in terms of why did it not show me the same thing that it did in the second heat. In the perfect world, the second and third heats should basically overlay each other exactly, right? Especially if you're using the same cooling rates for both of them, then it should look exactly the same, as long as your sample is stable, and you should be able to repeat that experiment. If you can't, then of course you would have to think about what actually happened and do your analysis accordingly. Okay, so that's basically why multiple heats are necessary.
So what's the meaning of changing the heating rate?
Changing the heating rate. So what essentially happens in that furnace? The entire block, that entire silver block, is heating up. So everything inside of that block is heating up. Okay. Now, if I heat it really, really slowly, then everything heats up essentially at the same time. Okay. Now, if I heat it up really quickly, then the heating block itself will get really, really hot, but everything inside is still kind of cold, right? So I sort of make the metaphor of like when you're doing barbecue and your flame's too hot, the outside is going to be burned, but the inside is going to be raw. So what happens is that there's a thermal gradient that gets formed between the sort of the outside and the inside, where whatever transformations that are happening in your sample typically need to happen gradually, right? As you heat up the sample so that you have an accurate number or an accurate analysis of that transition. So if you go faster, you're technically pushing or stretching that transition out over a larger temperature range. So you can possibly change sort of how things look on your data by changing your heating rate. Okay, that's why a lot of times I would tell people not to compare things that you ran on different heating rates unless that was your actual intention. Okay, so if I were to run the same sample with 3 different heating rates, it's very possible I can get three slightly different curves, or they look different, simply because of that thermal gradient issue. Okay, not necessarily because the transition itself is shifted per se, but the sample itself takes a longer time to get to that temperature because you're heating it so quickly. Okay, so by the time the furnace, for example, is at 200 degrees, your sample is only at 150. So it's now going through the transition, but you look at your raw data, it's going to say it's going to happen at 200 degrees. So it's a sort of a confusing thing to look at when you start changing your heating rate. Now, of course, sometimes you may want to do that for certain reasons. For example, I may want to cool my sample really, really quickly because I don't want it to crystallize. Okay, so that means I'm basically, quenching my sample completely. That's possible, okay, with certain samples. So in that way, changing my cooling rate can change what I see in my subsequent heating, because now I've quenched it completely and there's no crystals in there. So it's going to look completely different than if I quenched it at 5C per minute and I actually allowed it to crystallize itself. Okay, so it'll be 2 completely different experiments or 2 different sets of data that you'll obtain by just changing that cooling rate. Okay, but that's a really good question, because you don't want to sort of randomly choose these numbers. You want to make sure that you have some control and some understanding of where the numbers are coming from and why you're using those numbers before you get in and just kind of type in whatever. That's not really a good plan. So make sure that you sort of know and understand what you're trying to see from your material, how stable your material is, things like that, so that when you come here to do the DSC, you have an idea of kind of what you are expecting to see. Okay, that's a really good point. So going back to this,